D1. So this is one of the highlighting chemist problems. So you don't have to learn, you don't have to know anything about fluorescence in this class or anything. You don't have to know anything about Stokes shifts, but it's a neat problem that kind of relates energy and wavelengths and all that stuff together to kind of work on understanding the relationship between them. Because a very common problem that people run into is they if you're given two different wavelengths of light, the way that people instinctively just directly approach it is they'll take the two of them, they'll subtract them from each other, they're going to get a wavelength in whatever units, and they're going to convert that number into energy, but that number is actually going to be extremely wrong from the correct answer, because as I've mentioned before, right, the relationship between energy and wavelength is in an inverse, right? So the smaller that energy is, the higher the energy is going to be. Or sorry, the smaller the wavelength, the higher the energy is going to be. And so obviously, right, if you're subtracting two wavelengths, you're going to get a really small a number that's smaller than both of them. But then if you're directly converting that into an energy, right, that energy is going to be extremely high. So the way that you approach this right here is what a Stokes shift is and everything like that is just simply the energy between the excitation, or sorry, between the absorption and um, um, uh, the emission spectra, right? So fluorescence is that you're absorbing from one wavelength of light, and then through a few different pathways, that electron then relaxes down, and then one of those relaxation steps is actually emits an electron, or sorry, a photon within the visible region, typically. And so then that's what you see. So if you ever have used a black light poster or anything, the black light is actually in the near UV region, right? So it's pretty high in energy, and so it lights up whatever the ink is, and then that fluoresces off a different wavelength of light, right? Like green or blue or purple or red, whatever you have in those cases. But because the black light rate is outside of the visible region, you don't see that on the paper or anything like that, right? All you then see is just simply the fluorescent part. In those cases, right? So that's how fluorescence works in fluorescence paper. And so that energy difference, right, in that difference in wavelength between the wavelength that you absorb the photon at and excite the electron to is going to be different from the one where the electron actually relaxes down and emits a photon that you can actually see. And so the way to approach this problem, right, is that if you have something that is excited at 405 nanometers in this case, and then you observe the fluorescence at 561 nanometers, right? The Stokes shift in this case is going to be like what, 160 or 156 nanometers or something along those lines. Now I'm going to work it through incorrectly at first, right? So this is going to be the incorrect approach, and I'm going to to emphasize. Or actually, you know what? I'll work through it the correct way, and then I'll show you the incorrect approach, so that way you can see the difference, right? So the correct way, right, is the first step that you have to do is you have to convert both of those wavelengths into an energy unit, and we're just simply going to use joules, right? That's easy enough. So if we're looking at the energy of the absorption, right, so that's going to be this right here at 405 nanometers. So that's HC over lambda. So to do that, all we have to do is plug in all of our numbers. So we have 6.626 times 10 to the negative 34 joule seconds times the speed of light, which is 2.9979 times 10 to the 8th meters per second. And then the wavelength that we have is 405 nanometers, and so nanometers, right, has to get converted into meters, and so that relationship is 1 times 10 to the negative 9 meters per nanometer in this case. And so the energy that we get in joules is 6.626 times 10 to the negative 34 times 2.9979 times 10 to the 8th divided by 405 nanometers times 1 times 10 to the negative 9 comes out to 4.905 times 10 to the negative 19 joules. Right? I know that's more sig figs, but that's fine for right now. Right, so that's the energy of the absorption. The energy of the excitation is going to be the same approach, right? So HC over lambda. And so that rate is going to be 561 nanometers. So that is then 6.626 times 10 to the negative 34 joule seconds times 2.9979 times 10 to the 8th meters per second over 561 nanometers times 1 times 10 to the negative 9 meters per nanometer, right? Nanometers cancel, meters cancel, joules can't, or joules stay, seconds cancel. Right, so what we get is 561. So this value is 3.541 times 10 to the negative 19 joules, right? So that's the energy difference, you know, the energies of each one of them. So now what we're looking at, right, is what's the difference in energy between the two of them, right? So the difference in energy now is going to be equal to the energy of absorption minus the energy of excitation. So that will be 4.905 times 10 to the negative 19 joules minus 3.541 times 10 to the negative 19 joules comes out to 4.905 times 10 to the negative 19 minus 3.541 10 to the negative 19 comes out to being 1.364 times 10 to the negative 19 joules, right? Which I just simply had it one less sig fig in the answer key, right? So that's the value that you have right here. Right, so you have that in joules. You can just simply convert that into electron volts by multiplying by 1 electron volt divided by 1.60218 times 10 to the negative 19 joules, which is then equal to 1.364 times 10 to the negative 19 divided by 1.60218 times 10 to the negative 19 comes out to 0.85 electron volts, right? Which is, I think, what I have in the key. Yeah. Right. And so that's the way that you approach, right? So that's the correct way to do it. The incorrect way to do it, and so I'm just going to change color real quick. Right. So the incorrect way to do it is first to calculate the difference in lambda, right? So you have the lambda of absorption minus the lambda of excitation. So that gives you, 405 nanometers minus 561 nanometers, which comes out to being 405 minus 561 is negative 156 nanometers, right? So already, just having a negative number should probably, be a point where you're like, oh, that doesn't make any sense. But it could also very well be that somebody, is like, oh, well, I just simply flipped the two parts, so I'm not going to worry about that stuff. So either way, right? So we'll just use 156 nanometers, and so so we have that. So now all we have to do is just convert that into that wavelength into an energy, right? And so now we have our energy is going to be equal to, right, HC over lambda. So we plug in, right, we have 6.626 times 10 to the negative 34 joule seconds times 2.9979 times 10 to the 8th meters per second over our wavelength that we have here, right? So negative 156 nanometers times 1 times 10 to the negative 9 meters per nanometer, right? So seconds cancel, meters cancel, nanometers cancel. We only end up with joules. So we do that, we get negative, so we have 6.626 times 10 to the negative 34 times 2.9979 times 10 to the 8th divided by negative 156 times 10 to the negative 9th gives us a value of negative 1.273 times 10 to the negative 18 joules, or not negative 18, right? Sorry, negative 18. So it's times 10 to the negative 18 is the answer, right? Which is pretty much a full order of magnitude higher in energy than what we got in the previous part, right? And it's, essentially, 2 to 3 times higher than the energies of either one of the excitations. So that should be a trigger as to why doing it through that approach is incorrect, right? And why you're going to end up with a much higher value for the energy than what is correct. So again, the approach when you're working with figuring out the energy differences between two different photons or two different absorptions isn't to subtract the wavelengths of either of them, right? It's to first convert both of them into energy units and then use that difference to calculate what the the actual energy difference is. All right.